Hey guys, so today we are going to be in chapter 3, section 5, which is all about rational functions and their graphs. 3.5 works a lot like 3.2 did. 3.2 was all over polynomials and how to graph them. And in 3.2, we learned a lot of different tools and a lot of different things in order to do the graphing. Like we learned about maximum and minimum and about end behavior and multiplicity and all that stuff. And then we combined it all together in order to graph our polynomials. And today's going to work a little bit like that, where we're going to find all these different pieces and then we're going to stick them all together in order to graph our rational function. Now, one thing to note, which I've mentioned it a few times in the videos, but anytime in a math class that you see the word rational, you need to think that it's something that can be put into a fraction. So rational functions are quotients of polynomials. That means that you have a fraction, but you have a polynomial on top and a polynomial on bottom. Obviously, we don't want the polynomial on bottom to equal 0, so we do have to specify that. And if you remember back from 3.1, the domain of a polynomial is negative infinity to positive infinity. And that's true except for the points that make the bottom of our rational function equal to 0. So we will have to find these trouble spots, as I always call them, that make the bottom polynomial equal to 0. Because wherever that equals 0, we have trouble spots, and we can't include that in our domain. And so that's how we're going to start today. We're going to start simply by finding the domain of our functions. Remember, domain is all of the x values that you can put into a function to get out a solution. Domain of f of x equals x squared minus 9 over x minus 3. I'm going to go ahead and write out all three of the ones we're going to do, and then we'll just do them back to back. G of x equals x over x squared minus 9, and C is h of x, which equals x plus 3 over x squared plus 9. So these are the three different rational functions that we have, and we're going to find the domain for each of these. So the domain for a polynomial is negative infinity to positive infinity. But with rationals, we have to eliminate out whatever makes our denominator equal to 0. So really, in order to find the domain, you just have to find the trouble spots. And the trouble spots only happen where the denominator is equal to 0. So for each of these examples, I'm just going to look at the denominator and I'm going to set it equal to 0 and find out what values of x cause me to have problems. So for this first one, f of x equals 9 squared, x squared minus 9 over x minus 3. I need to find out where my trouble spots are. Well, my trouble spots are wherever x minus 3 equals 0. Well, to find that out, I'm going to add my 3 over, and I find that x equals 3. So when x equals 3, we have problems. And so we need to not have x equal to 3. Let me see if I move you over here. Maybe I can still see the whole. Yeah, I can. Good. So I need a little bit more writing room. Okay, so in my domain, I can't have the point x equals 3. So my domain is going to start from negative infinity, and I go all the way up until I hit my trouble spot. My trouble spot was positive 3. And then I use parentheses because I don't want to include that trouble spot. I union that with 3 to positive infinity. That is our interval notation. Now, we don't use set builder notation quite as much right now, but as a refresher, if we had to use set builder for this, that would be x such that x does not equal 3. That's another way of stating the domain. The top one is our interval notation. The bottom one is our set builder notation. We've done both throughout the semester. Usually we use the interval notation, but there's another refresher on set builder. So really we just need to figure out what causes issues in our denominator. So for b, we have g of x equals x over x squared minus 9. So I'm going to take that x squared minus 9, and I'm going to set it equal to 0. I'm going to add my 9 over. To get rid of a square, you have to square root. But when you square root a number, you have to remember the plus or minus. So this time we're getting two trouble spots. We have a trouble spot at -3 and a trouble spot at +3. So when we go to write our domain in interval notation, we're going to start the same way with -infinity and go all the way up until our first trouble spot. Our first trouble spot will happen at -3. And then you union that. And then you go -3. And instead of going off to infinity like we did up here, we have to go until we hit our next trouble spot, which happens at 3. Then you union, and then you go from your second trouble spot all the way to infinity. Here's something that's kind of helpful if you're unsure of how to write it in the interval notation. In our first example, we had one trouble spot and we had one union in our interval notation. In our second example, we had two trouble spots, and notice we have two unions in our interval notation. So that might help you remember to include that section where you're going from trouble spot to trouble spot. Again, if you wanted to see it in set builder notation, you'd have your set of x such that x does not equal -3 and x does not equal +3. All right, last example. We have c, which is h of x equals x plus 3 over x squared plus 9. To find the domain, I'm going to set the bottom, which is x squared plus 9 equal to 0. I'm going to subtract that 9 over. So I have x squared equals -9. To get rid of the square, I'm going to square root both sides. So I get x equals plus or minus the square root of -9. So at this point, either you're going to leave it like that, or you might be tempted to change that into plus or minus 3i, or you might just throw up your hands and say, I quit. Don't do any of those things. When you get to this point where we have the square root of a negative number, the question to ask is, well, is that a real number? No, that's an imaginary number. That's where we have our I. And so that means we're not going to have any trouble spots. You may even be able to recognize that just from looking at the very beginning, where we have x squared plus 9. Up here we had x squared minus 9. So there is some value or values that's going to give us 0 in our denominator. But down here, we have an x squared plus 9. So whatever number we plug in for x, it's going to become a positive number first, and then you're going to add another positive number to it. So if you're starting with a positive number and you add another positive number to it, can you ever get to 0? And the answer is no, because if you stick a negative number in here, it's going to be positive. Positive plus positive gives you a positive number. If you plug 0 in here, then you're still going to get positive 9 in the denominator. So there's no trouble spots for this one. There's no way to get a 0 in the denominator. So your domain stays -infinity to +infinity. There's no trouble spots here. So there's nothing that we have to eliminate out, and that's really nice. So that's how you find the domain. The domain is all the x's minus any trouble spots. The nice thing about this is the step that we just did, where we set the bottom equal to 0 in order to solve and find our trouble spots. These trouble spots are going to be our vertical asymptotes and our holes here in a minute when it comes time to graph. So that's actually really, really nice for us. Also, for this section, I did make like a little worksheet, but it's not really a worksheet that you fill out. It's just more of a lot of these notes, so you wouldn't have to copy them. If you wanted to print them off, you could, or if you're going to print that off, you might as well just print off my notes because it has all the examples worked out as well. But there was a little bit more, like it was a node heavy day. So there is a worksheet on there if you do want to look at that. So we were able to find the domain pretty well with our rational functions. Now what we're going to do is we're going to talk about arrow notation, which arrow notation is just a way to talk about what's going on in our graph. We talked a little bit, it wasn't arrow notation, but we did talk about end behavior with polynomials. We did that with the leading coefficient test back in 3.2. And that would tell us, you know, like if our graph was going up at the end and down at the front or whatever was going on. And that kind of helped us to have a mental picture in our head of what's going on with our graph. Well, that's what this arrow notation is really good for too. It kind of helps us to understand what's going on. And so these are the 4 different things. We talk about it in terms of X. We say as X approaches something, and then what's going on with our function. So as X approaches some number, and then notice this first one has a plus. That says as X approaches A, which is a number. So as X approaches this number from the right-hand side or from the positive side, then we would say something about our function. You can do the same thing for as X approaches A from the left, as X approaches infinity or increases without bound is another way that can be put, or as X approaches negative infinity or decreases without bound. So I know that's a little weird. So I'm going to do a really, really general example just so you can see how we would talk about a graph if we were using arrow notation. So here is a very, very general graph. I'm going to put asymptotes in here that lie right on the axes. So you may or may not be able to see them. I am using a different color, but that doesn't mean you can see it very well from the camera. But there's a vertical asymptote and a horizontal asymptote, which we will talk about here in a few minutes. Asymptotes are simply lines that your graph hugs. So here's my graph in yellow, like that. So now if I wanted to talk about my graph using these arrow notations, what I would do is I would look and I have 4 arrows. Notice that I have 4 arrows on my graph. So really I have 4 different things I could talk about using arrow notation. So this first one's over here. This arrow is pointing to the left. That means we are talking about as my x's get more and more negative. So the way I would write that is I would say as x approaches negative infinity, as my x's become more and more negative, then what is happening to my function? Or what is happening to my y's is the other way to think of that, because f of x is your y values. So as my x's are getting more and more negative, my y's are doing what? Well, they're going closer and closer and closer to 0. So my function or my y's are heading towards 0. That doesn't mean they're getting there, it just means that's where they're headed. So let's look at this bottom arrow. What are my x's doing here? So if I'm going this direction on my graph, then I am headed towards, well, I'm headed towards 0. So as my x approaches 0, and it's approaching 0 from what? Well, from the left side. So that's the negative side. So as x approaches 0 from the left, what is happening to my function? Or what is happening to my y's? So as I go this way, my function drops, and it drops fast. So my y's are heading off to negative infinity. As my x is approaching 0 from the left-hand side, my y's are shooting down towards negative infinity. So let's pop up here to this arrow of my graph. So as x is approaching what? Well, notice we have that vertical asymptote right there at y equals 0. So we approached that from the left. So So now let's approach it from the right. So as x approaches 0, from the positive side, my f of x, my function or my y values are doing what? Well, as I move this way, my graph is shooting way up to the positive infinity. So my f of x is going towards positive infinity. We have one more arrow to talk about, which is right here. So this is as x is approaching what? So as I'm moving this way, my x's are doing what? Well, they're getting more and more positive, and they're going to continue doing that. So as x approaches positive infinity, f of x, my function or my y values are doing what? Well, if you look, the more positive your x gets, the smaller your y gets. But your y is hugging this horizontal asymptote, which is at x equals 0. So they're getting closer and closer to 0. Now, does all of this information help us graph it? Not really, because the graph is already there. But it helps us talk about our graph and examine our graph in relation to the x's and the y's and what's going on at those different points. So it is a very useful tool. And you're going to see it here in a minute on the pictures that I draw for vertical asymptotes. And so it needed to be talked about. And that is a very general graph, but it is a nice graph to note. So let me slide this over. Vertical asymptotes. So in this graph, even though you kind of can't see it, there was a vertical asymptote that I drew in right there on the axis. That is a line where x equals some number, where your function increases or decreases without bound as x approaches it. That means that your graph is going to shoot up or shoot down as it starts getting closer and closer to that line. The way that I always think about it is my graphs are gonna hug my asymptotes. And so my graph gets closer and closer and closer to that asymptote, and it's gonna hug it. And it gets closer and closer and closer here, and it's gonna hug it. And the same thing is true for horizontal asymptotes, which we'll talk about in a few minutes. So here are the 4 general, versions of a vertical asymptote, where we have this vertical asymptote at x equals a, but then it's going to show you what happens as the graph is approaching it from different ways. So this first one on the upper left-hand corner, it says as x approaches a from the positive, so from the right-hand side, my function shoots off to positive infinity. The one right below that, though, the function could shoot off to negative infinity. That's okay. We're still approaching it from the right-hand side, so it still as x approaches a from the positive side. This right column, it's as x approaches a from the negative column, and notice our graph is going up in that first one and going down in the second one. But every time we do that, we have those vertical asymptotes. Now here's the nice thing about vertical asymptotes. Those are our trouble spots that we just found for our domain. So vertical asymptotes are where the denominator is 0 for our rational function when it is reduced or factored. That is the one stipulation. It needs to be reduced or factored. That means you have to do a little bit of algebra there at the beginning to make sure that it is reduced. Because there's going to be something that happens where sometimes things are going to reduce out. Like when you simplify a fraction, like 8 over 6, you can take out a 2 from both of those. That happens sometimes with these rational functions where you're going to be able to eliminate something, and sometimes that thing that you eliminate is going to cause a hole, because that's still a problem spot, but it doesn't show up as a vertical asymptote. It's going to show up as a hole. And so holes are values where the denominator of a rational function is 0, but does not necessarily result in a vertical asymptote. And I think that that is a little bit confusing, just how it is written and how it is displayed there. But we're going to do some examples, and it makes a lot more sense once you start seeing the examples. So stick with me as we are going to do vertical asymptotes, and I'll show you the difference between a vertical asymptote and a hole. So we're going to find vertical asymptotes, if there are any. And we're going to do 3 examples. we have f of x equals x over x squared minus 9. Then we're going to do g of x equals x plus 3 over, sorry, I didn't move around enough, over x squared minus 9. And then we're going to have h of x, which is x plus 3 all over x squared plus 9. These are going to be the three examples where we're going to find the vertical asymptotes. Okay, so like I said, finding vertical asymptotes is exactly like finding the trouble spots for our domain. The only thing is that you want to make sure that your fraction or your rational equation is fully reduced before you actually set the bottom equal to 0. So what you do then is you say, well, does x and x squared minus 9 have anything in common? If they have anything in common that you can eliminate, we need to do that first. Well, here's the thing, don't you do magic math. Don't say, well, yeah, there's an x and an x squared, so we can reduce that. No, you can't, because you have more than one term on bottom. And the second term, this negative 9, does not have an x. So you can't pull an x out of the bottom at all to eliminate with the top. So since it does not eliminate with anything, then you can just simply look at the bottom and set it equal to 0 and find the trouble spot. That trouble spot is going to be our vertical asymptotes. So x squared minus 9 equals 0. I'm going to add 9 to both sides, then I'm going to square root. So I get x equals plus or minus negative 3. Again, this is very similar to what we just did with finding the trouble spots for a domain, except now we know that at these trouble spots we have vertical asymptotes. So we have a vertical asymptote at x equals negative 3 and at x equals a positive 3. Vertical asymptotes will always be written as x equals some number because they're vertical asymptotes. Okay, so let's look at b, which is g of x equals x plus 3 over x squared minus 9. Again, we need to make sure that this is fully reduced before we do what we just did, where we set the bottom equal to 0 to find our trouble spots or find our vertical asymptotes. Well, you might be looking at that and saying, well, I can't reduce anything. But this is a special type of quadratic. We talked about it a few times, like back in 1.5 and back in chapter 2, where this is a difference of squares. And you may or may not recognize that. But a difference of squares is where you have something squared minus something squared. Because we could write this as x squared minus 3 squared. And if you can do that, then you have a difference of squares. And what that means is it's factorable. And it factors in the exact same way every single time, which is nice. It factors into x plus and x minus, and then the number that goes here is the number that you're squaring if you write it as a number squared. So instead of saying minus 9, it's minus 3 squared. So that factors into x plus 3 and x minus 3. If you don't believe me, think about it like this. If I FOIL this, then I get x squared and I get a minus 3x and a plus 3x. So that middle term goes away. And that always happens in a difference of squares. And so that goes away, and then I'm just left with the x squared minus 9. So you do have to be somewhat familiar with that so you can actually see if anything's going to reduce. Because when you write it like this, then you notice that you have an x plus 3 on top and you have an x plus 3 on bottom. That means those can simplify out to where you're left with 1 over x minus 3. And this is what we use to find our vertical asymptote. So then we're looking at this x minus 3, and we set it equal to 0 so that we know we have a problem at x equals 3. So we have a vertical asymptote at x equals 3. At x equals 3. But we can't just completely ignore this thing that we eliminated, because here's the deal. We eliminated that x plus 3, which would be the x equals minus 3 part. So if I plug in x is negative 3 into our original problem, I'm still going to have a problem, aren't I? So that eliminated out, but it doesn't eliminate the problem spot. It just makes it not a vertical asymptote. That's what it means in my notes when I say, if you have something that eliminates out, that's your hole. So right here, this x plus 3, that's where my hole happens. So I have a vertical asymptote at x equals 3, but I have a hole at x equals a minus 3. So just because we were able to simplify it out doesn't mean that it doesn't still cause problems for us in our graph. So if you're able to eliminate it out, you automatically know, okay, I'm going to have a hole there. I need to set that term equal to 0 and figure out where that hole happens. Okay? So now let's look at our last example. This h of x equals x to the third over x squared plus 9. Before we do any type of math, I want you to stop and think. That's always should be your first step anytime you approach math, is thinking. We did a problem just like this a few minutes ago with the domain, where we had x squared plus 9 on the bottom. And the question was there any trouble spots? Did we have to eliminate anything from our domain? No, we didn't, because there was no way to get 0 in the denominator. So if we can't get 0 in the denominator, then that makes our life really easy with finding the vertical asymptotes. Because if there's no problem spots, then there's no vertical asymptotes. And that makes it nice and simple for us if we're asked to find them. So this first one, we had 2 vertical asymptotes. The second one, we had a vertical asymptote and a hole. And this last one, we didn't have any vertical asymptotes. So that's nice. So as you saw in my really general graph earlier, we had vertical asymptotes, but we can also have horizontal asymptotes. Let me move that over a little bit. So a horizontal asymptote is a y equals a number, and that's where your graph approaches that specific number as your x increases or decreases without bound. So vertical asymptotes are when the function increases or decreases without bound. Your y's do. The x, or the horizontal asymptote, is when your x's are increasing or decreasing without bound. So the one thing that's slightly weird about horizontal asymptotes is you can actually cross them. So this third picture on the right, notice we have our graph and it comes actually through our asymptote and kind of bounces back and then it hugs. So we're still going to hug our asymptote. It could go through. It didn't change anything really in how we denoted or anything like that, but it's a little bit weird. We don't cross our vertical asymptotes, but you could theoretically cross your horizontal ones. I try to be nice and not give you those because I don't think they play by the rules, is how I have always looked at it. So I don't like them. But that's just me. There's nothing mathematically wrong with them. I just don't like them. So yeah, there's that. So with our vertical asymptotes, we just had to set the bottom equal to 0. With our horizontal asymptote, we actually have to learn some rules. And with finding horizontal asymptotes, what we're going to look at is we're going to look at the degree of the top polynomial or a numerator, and then we're going to look at the degree of our bottom polynomial or our denominator. And depending on what those degrees are, we have 3 different things that could happen. And so remember, the degree of your polynomial is the power, the highest power that it has. So if I was looking at the degree of this this rational function, my b, my g of x, I have an x to the first on top and I have an x squared on bottom. Excuse me. Excuse me. Chalk dust. So the top polynomial is a degree 1, and the bottom polynomial is a degree 2. And that's actually the case for all of our examples right here. But that's how you find the degrees. You're looking for the exponents. So there's 3 cases, like I said. If your top degree, your top equation has a degree that's smaller than your bottom equation, then you have a horizontal asymptote at y equals 0. There's nothing to compute. You just compare the top degree with the bottom degree. If the top's smaller, it's y equals 0. If the top degree equals the bottom degree, then you have a horizontal asymptote at this y equals an plus am. Those are your leading coefficients. So let me cheat real quick, and because we're going to do some examples, but just so you have a quick thing right here. Let's say that said x squared and x squared, okay, for this example. Those are equal then. So then I would look at my leading coefficients. Well, the coefficient on top is 1, and the coefficient on bottom is 1. So I would have a horizontal asymptote at y equals 1, because 1 over 1 is 1. That's going to make a little bit more sense in a minute when we actually do our examples. If the third way is if the power or the degree of the top is greater than the degree of the bottom, then you're not going to have any horizontal asymptotes at all. So if the top is smaller than the bottom, you have a horizontal asymptote at y equals 0. If the top equals the bottom, then you look at your leading coefficients, and that's where you have a horizontal asymptote. If the the top is greater than the bottom, then you have no horizontal asymptotes at all. So I'm going to leave that up so you have that to reference while I write our examples on the board. So this time we're going to find horizontal asymptotes. And we have f of x equals 4x over 2x squared plus 1. We have g of x equals 4x squared over 2x squared plus 1. And then we have h of x equals 4x to the third over 2x squared plus 1. And we're just going to find if we have any horizontal asymptotes or not. And the way we do that is we're going to look at the degrees of these various polynomials. So for A, I'm going to look at the degree of the top and compare that to the degree of the bottom. So the degree of my top polynomial, that 4x, that x doesn't have a power, so we understand that to be a power of 1. So my n is 1. The degree of the bottom, 2x squared plus 1, is 2, because it has a power of 2. That tells me that my n is less than my m. When my n is less than my m, then I have a horizontal asymptote at y equals 0. Okay, let's do g of x, which is 4x squared over 2x squared plus 1. The degree of the top for 4x squared is 2, and the degree of the bottom for 2x squared plus 1 is also 2. So I have n equals n. So when the top degree equals the bottom degree, then I'm going to look at my leading coefficients. My leading coefficients in this case are 4 and 2. So that means I have a horizontal asymptote at y equals 4 over 2, which is simply 2. That's how the leading coefficient bit works. Our last example is h of x equals 4x to the third over 2x squared plus 1. So I need to know the degree of my top and the degree of my bottom. The degree of my top is 3, and the degree of my bottom is 2. So that means my top has a greater degree than my bottom, which tells me I have no horizontal asymptotes. If If my top is greater than my bottom, then there's no horizontal asymptotes at all. So that's how you find those. One thing that I do want you to note, and I will change colors so maybe it'll stand out a little bit. What if we had kind of this little bonus function where I had 4 over 2x plus 1? What is the degree of that top function? Hopefully you said the degree is 0. And if you did, that is correct. Because notice there's no x, there's no variable, and there's no exponent. But you could write it as x to the 0th power because anything to the 0th power is 1. So then you would compare 0 to 1, and we could still then compute our horizontal asymptote, even though the top was just a number. So don't forget about that as you work through these problems. Just because there's not an x raised to an exponent doesn't necessarily mean that you can't do it or there's no horizontal asymptote or anything like that. Okay? So we have all of these new pieces to play with that's going to help us to graph these equations. I'll go ahead and warn you that these equations are going to take a little bit of space on the board. And so I'm going to have to move you around to where you're not going to be able to see the full thing. But remember, you can always pull up my notes, which is what I have up here for you, but you could pull them up on your own and you'd have my whole problem before you as I am working this out, because I'm going to have to take you in segments through this problem. Okay? So how do we graph a rational function now that we know how to find all of this information? Well, the first thing that is good to do is to see if we have any symmetry. When you have symmetry, that means you could fold your graph a certain way and it's going to lay right on top of itself. So we do this by plugging in negative x into our function and seeing what we get. If, when we plug in negative x into our function, if it equals the same function that we started with, then we know we're symmetric about the y-axis. That means that we could take our graph and fold it about the y-axis like this, and it would lay right on top of itself. If we plug in negative x into our function and we get negative of our original function, then that means we are symmetric about our origin, which means we would take our top corner and fold it down to our bottom, and it would lay right on top of each other that way. If that's not true for either of those, then that means we're not symmetric about the y-axis or our origin, and that can happen, and that's okay. Does this symmetry help us a ton with graphing? A little. It helps you to have a little bit of a better picture in your head, maybe, of what's going to go on, but it's not integral to it. When we do these in exams, I don't usually ask you to find the symmetry, but it's good to note how to find the symmetry. And you find the symmetry by plugging in negative x into each equation and figuring that out. After you've done the symmetry, step 2, you're going to find the y-intercept if there is one. And we do that the same way we've done it all year long, where we plug in 0 for our x and we solve. After that, we're going to find our x-intercepts if there are any. And we do that by setting the top equation equal to 0. So that's p of x. Because remember, our general form says p of x over q of x. So p of x is your top equation. So we set that equal to 0 and solve, and that tells us if we have any x-intercepts. Step 4 is find the vertical asymptotes, and we do that by setting the bottom equation equal to 0. So we set the top equation equal to 0 to find our x-intercepts. We set the bottom equation equal to 0 to find our vertical asymptotes. Then we find our horizontal asymptotes by comparing the degrees, and then we're going to put all of that information on a graph, and then we're going to plot at least one point between and beyond any x-intercept and any vertical asymptote. So we're going to do some test points to make sure we know what's going on in our graph as we're graphing it. And then step 7 is to graph it. So that is a lot of steps, but they all kind of just fall into place. On exams and things like that, I don't want you to stress out that you have to remember all 7 of those steps. You'll be asked for each of those steps as you work through the problem, but you do have to understand enough in terms of how to do that. So it's going to say find the horizontal asymptotes. It's not going to tell you how, but it's going to tell you to do it. And so you do have to understand how to do these things, not necessarily remembering step by step when you're supposed to do it. All right, so we are going to graph f of x equals 2x minus 1 over x minus 1. This is going to be our first graph. And we're going to do all of the steps, and I'm going to label them, and we're going to go through them so you can see how it all works. So step 1 is symmetry. Symmetry is where we're looking at f of negative x. That's where we plug in negative x into our equation and see what we get. Hopefully now it won't turn off anymore because there's not enough movement in the classroom or whatever. Okay, so we have negative 2x minus 1 over negative x minus 1. So the question is, does f of negative x equal f of x? Does this right here equal our original equation up there? Well, the answer is no, because we have a negative in front of our 2x and a negative in front of our x, and we don't have that in our original equation. So f of negative x does not equal f of x. So we're not symmetric about the y-axis. That's what we found out. We are not symmetric about the y-axis. So what about f of negative x? Does that equal negative f of x? If we took negative 1 times our function, would that be what's in our box? Well, I'm not sure. So let's take negative 1 times our function. That would give me a negative 2x plus 1 all over x minus 1. Does this equal what we had? The answer is no, because we have a negative 2x, and that's a negative 2x, which is good, but we have a plus 1 here and a negative 1 here, and then we have a plus x here and a minus x here. So no, these are not equal. So we are not symmetric about the origin. So we're not symmetric. That's all we found out. Okay, great. We're not symmetric. So step 2, we are going to find the y-intercept, and we do that by finding f of 0. That's where we plug in 0 for all of our x's. So we have 2 times 0 minus 1 over 0 minus 1, which equals negative 1 over negative 1, which equals 1. So we have a y-intercept at 0, positive 1. So we found that we're not symmetric. We found our y-intercept. Sorry to move you, but you gotta have more space. So now let's find our x-intercept. We find our x-intercept by taking our p of x, or our top equation, and setting it equal to 0. So in this case, our top equation is 2x minus 1 equals 0. So I'm going to add that 1 over, divide by 2, and I find x is a half. So I have an x-intercept at a half 0. Step 4 is where we find our vertical asymptotes. And we do that by setting Q of x, or our bottom equation, equal to 0. So in this case, that's x minus 1 equals 0. So we have x equals 1. So I have a vertical asymptote at x equals 1. Okay. Step 5. Try and leave some of these steps up there that are ahead of me. Step 5 are horizontal asymptotes. Horizontal asymptotes is where we look at the degree of the top versus the degree of the bottom. So I'm going to rewrite the function just so it's here in front of you, which is 2x minus 1 over x minus 1. So I need the degree of the top and I need the degree of the bottom. Well, the degree of the top is 1 and the degree of the bottom is 1. So when the degrees are equal, then I have a horizontal asymptote at y equals, and then I look at my leading coefficients. My top coefficient is 2 and my bottom coefficient is 1. So that's 2 over 1, which means I have a horizontal asymptote at y equals 2. Now with all of this information, I'm able to start finally putting some stuff on a graph so I can figure out what my test points need to be. Because step 6 is really about taking test points and then graphing. But I find it's easier to find the test points after you've put some of this information on a graph. So let's get some of this on a graph. Okay, so we found that we had a y-intercept at 0, 1. We have an x-intercept at a half, 0. We found that we have a vertical asymptote at x equals 1. Remember, vertical asymptotes are lines that your graph is going to hug. We have a horizontal asymptote at y equals 2. Again, horizontal asymptote, your graph is going to hug it. Excuse me. So if we're looking at this, I don't have a lot of information right now. I have 2 points and 2 lines, and that's not a lot. But I know that my graph wants to hug my asymptotes. So I can logically think, okay, so it's going to hug over here, and probably it's going to shoot over here and hug right there too. But I'm going to test that. I'm going to make sure of that before I put it on my graph. And so that's what it means. I found that there's a y-intercept, so I'm going to pick another point over here to the left of my y-intercept, and I'm going to test that. So let me make my table where I have x, I have f of x equals 2x minus 1 over x minus 1, and then I have my y. And yes, I know I went off the screen. I'm going to have to angle you a little bit. There you go. So I'm going to pick a point over here to the left of my y-intercept, and I'm going to test that point. So I'm going to test the point -1, and I'm going to see what I get. And I do that, I'm going to plug it in, so I have -2 minus 1 all over -1 minus 1, which is -3 over -2, which is positive 3 over 2 when it's simplified. So now I have another point that I can graph. At -1, my graph is at 3/2, which is 1.5. So look at that, it's kind of doing what we thought it was going to do. It came up, and then we know it wants to hug that asymptote. So I'm going to go ahead and just draw that out. You could keep testing points if you wanted to make sure of that, but that's what it's going to do. So we know this part, but we don't know if it does anything over here to the right-hand side of this vertical asymptote. And so I'm going to pick a couple of points to test. That's what it means when you need to plot at least one point beyond your vertical asymptotes. It's always better, like if there's nothing over on part of your graph, always better to pick a couple of spots. So I'm going to do the 0.2 and the 0.3 over here to figure out what's going on with my graph. So at the 0.2, I have 4 minus 1 over 2 minus 1, which gives me 3 over 1, which gives me 3. So that gives me the 0.23. At 2, I'm up here at 3. Because see, if I only did one test point in that spot, I don't really know what's going on. So I'm going to do that other one, that 3, and test it. So if I plug in 3, that'll give me 6 minus 1 over 3 minus 1, which gives me 5 over 2. 5 over 2 is 2.5. So at the 0.3, I'm at 2.5. So notice that's lower than the first point. And since I want to hug my asymptotes, and since I know what's going on over here, I can pretty well deduce that I'm going to hug here and hug like that over there. If you wanted to make doubly sharp, you could pick a point between 1 and 2 to make sure that you do shoot up like that, but there's really not a lot of other options for that one. So that's what it means to take the test points. And then this graph is complete. We have our asymptotes, we have our points, we did some test points to figure out the missing information, but we were able to successfully graph that rational equation or function. So it is a lot of steps, but each step in and of itself is not algebraically super difficult. We are going to do one more example that's a little bit more complicated, but it's not horrible. But I want to make sure and get through that example as well. So I'm going to erase most of the information that I have on the board. I'm going to leave up some bare bones so that I don't have to write absolutely everything again. All right, let's do one more example so that we can have a better grasp of how to do all these steps. Okay. Oh no, that's my paper. All right. This time we are going to graph f of x equals 3x squared over x squared minus 4. That's the function that we want to graph. So the first thing we're going to do is see if we have any symmetry. And we do that by plugging in negative x into our equation. So that'd be 3 times negative x squared over negative x squared minus 4, which equals 3x squared over x squared minus 4. So f of negative x, does that equal our original equation? Is this the same as our original equation? Yes, it is. So that means we are symmetric to the y-axis. So that worked out. We're actually symmetric this time. We weren't last time. Step 2, we're going to find the y-intercept. We do that by finding f of 0, where we put 0 into our equation. Anywhere that there's an x, 0 over negative 4, which is 0. So I have the point 0, 0. If I find that my y-intercept is 0, 0, I kind of already can cheat a little bit, and I know I'm going to have at least one x-intercept at 0, 0. But I need to still do the problem to make sure that there's no extras anywhere else. So to find the x-intercept, that's where I take p of x equal to 0. That's my top equation. So my top equation was 3x squared, and I set that equal to 0. I would divide both sides by the 3, which gives me x squared equals 0. You square root both sides, so you get x equals 0. So we still just find that our one and only x-intercept is at 0, 0. Step 4 is finding the vertical asymptotes, and we do that by setting q of x equal to 0. That's our bottom equation. So we have x squared minus 4 equals 0. X squared equals 4. I added the 4 over. Now I'm going to square root both sides to get rid of that square. So I get x equals plus or minus 2. So what does that tell me? That tells me I have a vertical asymptote at x equals negative 2 and at x equals positive 2. So I have 2 vertical asymptotes, which is a little bit different because last time we only had 1. That's why I wanted to make sure and work this problem as well. And remember, if at any point I move too fast, luckily you're watching this online, so you can always hit the pause button and get caught up. Horizontal asymptotes. Let me go ahead and write the function again, just so we have it here in front of us. 3x squared over x squared minus 4. I need to look at the degree at the top over the degree at the bottom. So the degree at the top is 2, and the degree at the bottom is 2. When they are equal, then I'm going to have a horizontal asymptote at y equals, and then I have to look at the leading coefficients. So the leading coefficient on top is 3, and the leading coefficient on bottom is 1. So 3 over 1 simplifies down into 3. So I have a horizontal asymptote at y equals 3. Now that I have all of that wonderful information, I'm able to go ahead and put all of this stuff on a graph and then start being able to find where I need my test points. So I'm going to draw my graph. Here, I know that I had a y and an x-intercept at 0, 0. I know that I have vertical asymptotes at negative 2 and at positive 2. I know I have a horizontal asymptote at y equals 3. And that's really about all I know. And I know I'm symmetric about the y-axis. So if I fold my graph left to right on top of itself, it's going to lay on top of each other. So notice this graph. Notice it's different than the graph we did just a minute ago, because the graph that we did just a minute ago, we had one vertical asymptote and one horizontal asymptote. So it only cut our graph into 4 quadrants. Now we have really 6 different spots, because we have over here and up here and up here and up here and over here and over here. And right now we only have 1 point. That's all we have. So we're going to have to test a whole bunch of points to figure out what's going on over here. So I'm going to pick 2 points to the left of my vertical asymptote. I'm going to pick a point between my vertical asymptote and my intercept. I'm going to pick up another point between my intercept and the next vertical asymptote. And then I'm going to pick 2 points over here to the right of my vertical asymptote. That way I have a good smattering of what's going on pretty much everywhere in my graph that I could possibly think to put stuff. So let's move you over. Sorry about that. So that you can see the graph and my table. So I'm going to do another table. I'm going to have an x, then I have f of x, which equals 3x squared over x squared minus 4. And then I have my y column. So I said I'm going to pick 2 points over here to the left of my vertical asymptote at x equals negative 2. So I'm going to pick the point negative 4 and negative 3. I'm also going to pick a point between my asymptote and my intercept. So the logical one there is -1. I said I'm going to pick a point between my intercept and my next asymptote. Again, logically, we would have 1. And then I need to pick up 2 points at least past my last vertical asymptote at x equals 2. So I'm going to pick the points 3 and 4. Notice they kind of mirror each other, which is nice just for computing what these values are. So I'm going to start with -4 and plug that in, where I have 3 times 16 over 16 minus 4, because -4 squared is 16. That equals 48 over 12, which is 4. So at -4, I'm up at 4. Okay, it doesn't tell me a whole lot, but I do have another point now on my graph. So let's do 3. 3 times 9 over 9 minus 4 is 27 over 5. 27 over 5, that's like 5 2/5. So it's almost 5.5, which I didn't go quite up high enough on my graph to do 5.5, but there's 5.5. So notice if we connect those, and if we remember that our graph wants to hug its asymptotes, then we can kind of do this and shoot off up there and do that. We know that that's what's going to happen in that section of our graph. Okay, at -1, we have 3 times 1 over 1 minus 4, which is 3 over -3, which is -1. At 3 times 1, like we plug in 1, 1 squared, squared, so we get the exact same thing, which is 3 over -3, which is -1. So that's nice, but that also plays into the fact that we know that if at -1, we're down at 1, since it's symmetric to the y-axis, then it makes perfect sense that at +1, it's also going to be down there at -1, because if we folded the graph over, then it would have to lay right on top of each other. And since we still have to hug our asymptotes, we know then that we're going to have this upside down parabola right there in the middle. And then here's kind of a logical question. If when I plugged in -4, I get +4 because I'm squaring my answer, then what's going to happen when I put in +4? I'm going to get the same thing. So when I put in +4, I'm going to get 4 out. And when I put in +3, well, look up here, I'm going to get 27 over 5. So I actually don't have to do the math on those because I know that it's symmetric. It's going to give me the same values. So at +3, I'm up at 5.5 again. And at +4, I'm at 4. So I know that my graph is going to do this because it is symmetric. So that's where it is kind of helpful to know at the very beginning that we are symmetric to the y-axis, because I don't have to do quite so much algebra over here on my table. So this graph is about as hard as you will encounter in my class, where you have 6 different sections or regions of the graph, and we have to kind of figure out what's going on. But again, the fact that it was symmetric is good. And even if you'd forgotten or you hadn't tested for symmetry, by plugging in the values, you would have been able to figure out what's going on. And that is the end of 3.5.